In my number of paths video, we looked at finding the number of paths between two nodes. However, there are situations where we might not care about the number of paths between two nodes. In this video, we'll look at the situation where we find the shortest path between nodes. Specifically in this video, we'll look at what the shortest path is, finding the shortest path, and the Dijkstra's shortest path algorithm. A shortest path problem is a problem where we must find the shortest path between two nodes on a network. A shortest path problem doesn't have to involve finding the shortest distance between two nodes. We may also be interested in finding the quickest path, which minimizes time, or the cheapest path, which minimizes cost. To find the shortest path, the edges or arcs need to be assigned a weight, which could, for example, represent distance, speed, or cost. When we travel somewhere, like from home to work, we're usually interested in determining what is the shortest, quickest, or cheapest way to get there. In my network video on the number of paths, we established that there were 6 paths between home and work in this network. This time, we've assigned weights to the arcs. This is a directed graph or a digraph, so you cannot move backwards along any of these streets. One method to solve this problem is to find the total length of every route and determine which is the shortest. If we do this, we get 13 units for A, 8 units for B, 11 units for C, 8 units for D, 11 units for E, and 6 units for F. In this case, the shortest path between home and work is F, with a total distance of 6 units. Although an exhaustive search is a valid way to find the shortest path, it becomes increasingly tedious when the networks are large and complex. The mathematician Dijkstra devised a more efficient algorithm for large networks. The process is as follows. Step 1. Assign a value of 0 to the starting node. Draw a box around the node label and the 0 to indicate the label is permanent. Consider all unboxed nodes connected to the node you've just boxed. Label them with the minimum weight from the starting node via the set of boxed nodes. Choose the least of all unboxed labels on the whole graph and make it permanent by boxing it. Repeat step 2 and 3 until the destination node has been boxed. Then you've got to backtrack through the set of boxed nodes to find the shortest path through the network. Note, majority of the nodes will end up with boxes around them, and all of the nodes will have the shortest path to that node labeled in them. Let's look at finding the shortest path from A to O using the algorithm. Assign a value of 0 to the starting node. Draw a box around the node to indicate that it's permanent. Consider all unboxed nodes connected to the node you've just boxed, that's B and F. Label them with the minimum weight from the starting node. So B is 2 and F is 1. Now we choose the least of all unboxed labels on the whole graph and make it permanent by boxing it. That's F, which is 1. Now we consider all unboxed nodes and connected to the node you've just boxed, they are G and K. Label them with the minimum weight from the starting node via the set of boxed nodes. G is 1 plus 2, which is 3, and K is 1 plus 4, which is 5. Now we choose the least of all of the unboxed labels on the whole graph and make it permanent by boxing it. In this case, it's B. Consider all of the unboxed nodes connected to the node we've just boxed. The only one that's not labeled at the moment is C, so we label it with a weight of 5. Choose the least of all unboxed nodes and make it permanent by boxing it. This time it's G. Now we consider all of the unboxed nodes connected to the node we've just boxed. They are H and L. And we label them with the minimum weight from the starting node via the set of boxed nodes. So H becomes 6 and L becomes 8. Now we choose the least of all unboxed labels on the whole graph and make it permanent by boxing it. This time C and K have equal weight. I'm going to start with C, but we could have chose either. Now we consider all unboxed nodes connected to the node we've just boxed. That's D and H. We label D as 10, which is 5 plus 5 is 10. H has already got the minimum weight. If we went through C, it'd be 5 plus 6, which would be 11, which is greater than 6, so we'll leave H as 6. Now we choose the least of all unboxed nodes again. This time it is K, and we make it permanent by boxing it. Now we consider all of the unboxed nodes connected to the node we've just boxed. The only unboxed node is L, which is labeled 8. This isn't the minimum weight if we go through K. So we cross out 8 and we write 7. That's 5 plus 2. So now the minimum weight for L to get to L is 7. Again, we choose the least of all unboxed nodes on the graph and make it permanent by boxing it. This time it's H. So now we consider all of the unboxed nodes connected to the node we've just boxed. That's I and M. we label them with the minimum weight from the starting node via the set of box nodes. For I, it's going to be 8, 6 plus 2. For M, it's going to be 6 plus 1, which is 7. Now we choose the least of all unboxed labels on the whole graph and make it permanent by boxing it. I've chosen L. Consider all unboxed nodes connected to the node you've just boxed. The only one is M. This is already labelled with 7. If we go through L, it would be 9, so we leave it as 7 because we're looking for the shortest path. Choose the least of all the unboxed node labels on the whole graph and make it permanent by boxing it. This time we choose M and we box it. Consider all unboxed nodes connected to the node we've just boxed. The only one is N, and it's connecting through M, so we write 11 for N. Choose the least of all the unboxed labels on the whole graph and make it permanent by boxing it. This time it's I. Consider all unboxed nodes connected to the node we've just boxed. Label them with the minimum weight from the starting node via the set of boxed nodes. D is 10 if we go through I, so we leave it as 10. We change N to 10 because if we go through I, 8 plus 2 is 10, which is less than 11. Then we can label J with 8 plus 1, which is 9. Now we choose the least of all the unboxed nodes. This is J, so we put a box around it and make it permanent. Now we consider all the unboxed nodes connected to J. That's E and O. So 9 plus 3 is 12 for E. 9 plus 4 is 13 for O. Choose the least of all unboxed labels on the graph and make it permanent by boxing it. I'm going to go through D just to make sure. Consider all the unboxed nodes. The only one is 12. If we add 2 to 10, we would get 12, so we just leave it as 12. Choose the least of all the unboxed labels on the whole graph and make it permanent by boxing it. This time it's N. Now we consider all of the unboxed nodes connected to N, and the only one is O. If we travel to O from N, we go 10 plus 2, which is 12, so we cross 13 out and we write 12. We've reached O, so we can make it permanent by boxing it. Now we've got to backtrack through the set of boxed nodes to find the shortest path through the network. So we start at O, and we go, we just did it, so we know 12 take 2 is 10, 10 take 2 is 8, 8 take 2 is 6, and we're just working out which edge or arc we had to follow in order to get the value in the node. If we went left, 6 take 3 is 3, so I think we'll do that because it's going to make the shortest path. And then we go 3 take 2 is 1, and 1 take 1 is 0. Now we've found the shortest path. Working backwards, we get O goes through N, I, H, G, F, and A. So the shortest path is A, F, G, H, I, and O. Let's look at another example where we find the shortest path from A to G. We assign a value of 0 to the starting node. Draw a box around the node and the node label to indicate that it's permanent. Now we consider all the unboxed nodes connected to the node we've just boxed, and we label them with the minimum weight from the node we've just boxed. So that's 4 for B and 9 for C. So we choose the least of all the unboxed labels on the whole graph and make it permanent by boxing it. It's going to be B. Consider all the unboxed nodes connected to the node we've just boxed. That's F, D, and C. Label them with the minimum weight from the starting node via B. It's going to be 19 for F, 15 for D, and if we went through B, for C we'd actually get 8, so we cross out 9 and write 8. Now we choose the least of all the unboxed labels on the whole graph and make it permanent by boxing it. That's C. Now we consider all the unboxed nodes connected to C. That's D and E. We label them with a minimum weight from C. So that's going to be 10 for E. This time, if we go through C to D, we actually get 14. So we cross out 15 and we write 14. Now we choose the least of all unboxed labels on the whole graph and make it permanent by boxing it. This time it's E. Consider all of the unboxed nodes connected to E. We label them with a minimum weight from E. We'll look at D first. If we go 10 plus 3, it's actually going to be 13, which is less than 14. So we cross out 14 and write 13 in D. The other node connected to E is G. We go 10 plus 16, it's going to be 26 for G. Now we consider all of the unboxed nodes again, and we put a box around the node with the lowest value, which is D. Now we consider all of the unboxed nodes. If we go through D this time, we're going to get 13 plus 5, which is 18. So we cross out 19, we write 18 in F. F is the least of all the values with the unboxed nodes, so we box it. Now if we go to G through F, get 18 plus 7, it's going to be 25. So we cross out 26 and we write 25 in G, and we put a box around it. Now we've reached G. Now we have to backtrack through the network in order to find what the quickest path was. So we go 25. If we took 16 from it, we wouldn't get 10. So we go 25 take 7. That tells us that we go back to F. Now from F, if we took 15 from 18, we wouldn't get 4. So we go 18 take 5, we would get 13. So we know we go back to D. From 13, we take 3, we go back to E. E, we take 2, and we get to C. C, we know if we took 9, we'd be in negative, so we don't go back to A from there. We've got to go 8 take 4 is 4, back to B. And then from B, we go to A. So the quickest path in reverse is G, F, D, E, C, B, A. And we can add them up. We know the shortest path is going to be 25, and that's from A, B, C, E, D, F, G. In summary, in this video, we've looked at what the shortest path is, finding the shortest path, and Dijkstra's algorithm. Thank you.